Hello, my name is David Brown. I'm an Associate Director at the Steel Construction Institute, and this presentation will give an overview of the analysis and design of portal frames. In this presentation, we'll consider the advantages of this very popular form of construction and the main elements of a portal frame structure. And then, even if final design is going to be completed by a steelwork contractor, we may well want to have an idea of the likely member sizes, or we might want sizes for an initial analysis. So I'll discuss how we can quickly establish preliminary sizes for the rafter and for the column. And then we'll consider analysis, not in depth, because I anticipate that almost all analysis will use software. There are, however, some important modelling issues, such as how we model base stiffness, and I'll cover those points. Portal frames are very likely to be sensitive to second-order effects, but the general Eurocode rules for assessing frame stability are not immediately appropriate for portal frames, so I will explain the recommended alternative. And then, once we've established forces and moments around the frame, and possibly amplified those forces to allow for second-order effects, we can then proceed to the calculation of member resistances. And at that stage, the location of the restraints will be very, very important. It may be that we judiciously position those restraints, and it's absolutely essential that the design assumptions are realised in the details, and I'll emphasise the key issues. I'll give an overview of the design issues if we have a boundary condition and we need to consider fire design, and then finally I'll consider the serviceability aspects of portal frame design. Portal frames are very common. They're very cost effective, they're very structurally efficient, they are lightweight, and that lightweight is both the superstructure and the foundations. There are mature design rules, especially in BS 5950, which has sections specifically devoted to portal frame construction. They're almost always designed using bespoke software, so they really are a highly efficient design. And in addition to the structural issues, there is a very competitive supply chain, which is all good news for the final client. And these advantages mean that portal frames take a huge share of the single-storey market. Over 90% of the single-storey market is occupied by steel portal frames, and some 45% of the constructional steel used in the UK goes into portal frame construction. So they really are a very significant form of structure. When people talk about portal frames, often they have in the back of their minds a shed sort of construction. It doesn't need to be so. The exterior views, as shown, can be very attractive. There are lots of opportunities to prepare a design with aesthetic appeal. The main elements in a portal frame structure then are first of all the main frames, spanning from column to column. There is no bracing within the plane of the frame. Secondly, the gable frames, which might be a portal frame, especially if extension is anticipated at some point in the future. The alternative is that the gable frame is constructed from gable columns and simply supported rafters, and if no extension is anticipated, this is the likely form of the gable, and it's chosen because it is a lighter weight solution. There will be bracing in the roof, which carries the loads from the gable columns to the eaves. There will be bracing in the longitudinal elevations, which carries the loads to the foundations, and it also provides stability for the portal frames. And there may be bracing in the gable. Bracing in the gable is only required if the gable is constructed from gable columns and simply supported rafters. If the gable frame is a portal frame, then no bracing in that frame will be required. Then there is the secondary steelwork, the purlins and side rails, and the term secondary is rather an unfortunate term because the so-called secondary steelwork is very important and it's used for restraining the primary steelwork. Finally, there is the cladding, which provides the watertight envelope, and may also be designed as a thermal and an acoustic barrier. Typical sizes then are that spans range anywhere up to 50 metres. The eaves height might be anywhere between 5 metres and 12 metres, though these days a taller frame is quite common. In terms of roof pitch, 6 degrees is almost universal, and frame spacing might be anywhere between 5 metres and 8 metres. And again, in modern construction, the larger bay centres is more common. There are many variations on the portal frame theme. There is no need to have a plain gable to the end of a portal frame structure. It could be a hipped roof, where there is a slope both to the eaves and to the gable. Parapets can be provided, which serve to disguise the roof line altogether. Multiple spans are very common indeed, and within multiple spans then the use of hit and miss frames are very common. In a miss frame, the intermediate column is omitted, and this provides a larger area of column free space and gives more flexibility to the end user of the structure. The loads from the miss frame are carried to the hit frames via a valley beam. It would be common to provide a hit frame every other frame or maybe every third frame, and both of these would require a substantial valley beam. The rafters in a portal frame are always haunched, and the haunch does a very important job. First of all, it reinforces the rafter in the area of a high bending moment. So the length of the haunch is chosen so that the bending moment at the sharp end of the haunch is approximately equal to the bending moment adjacent to the apex. And this means that we can choose a lightweight rafter which is working very hard over its entire length. The second advantage of a haunch is that it delivers longer lever arms to the tension bolts, and therefore we can produce an efficient connection. And finally, the addition of a haunch adds stiffness into the frame, and adding stiffness tends to reduce the deflections. The eaves haunch is usually modelled in analysis, usually by a series of short members, each with a varying inertia. In contrast, the apex haunch is usually not modelled. It may be haunched as shown, or for smaller spans might simply be an extended end plate. And the smaller detail is possible because the bending moment at the apex is much smaller than the bending moment at the eaves. Bases in the UK will generally be assumed to be nominally pinned and modelled as that in analysis. A nominally pinned base avoids the cost of a moment resisting base, and perhaps even more importantly, avoids the cost of a moment resisting foundation. Despite the assumption that the base will be nominally pinned, it's common to provide 4 holding down bolts, and clearly a base such as this has some stiffness, and it's usual to take benefit of that stiffness when analysing the frame, particularly when assessing frame stability and when calculating the frame deflections. The guidance on modelling the stiffness of a nominally pinned base is that when calculating alpha crit, which we'll see a little bit later, which is the measure of frame stability, then to model the nominally pinned base assuming it has a stiffness equal to 10% of the column stiffness is recommended. When considering deflections, to model the nominally pinned base assuming it has a stiffness of 20% of the column is recommended. However, when calculating at ULS to determine the forces and the moments around the frame, to model a frame with a perfect pin at the base is very highly recommended, because otherwise the resulting moments need to be carried through the base plate and on into the foundations. There are generally 3 types of bracing. There is the roof bracing, which collects point loads from the gable. It also collects any axial load in the purlins, and that axial load might be from wind drag on the roof, or might be the restraint forces which arise in the purlins as they restrain the primary steelwork. There will also be bracing in the longitudinal elevations, which carries those forces to the ground. There will possibly be bracing in the gable end, although this is not needed if the gable is a portal frame. Moving on out to the secondary steelwork, the purlins and the rails, they're generally cold rolled. They are thin gauge material. There are a variety of profiles and there are a variety of systems. It may be that the purlins and side rails are designed as simply supported and they span frame to frame. Or it may be that the system utilises the benefit of continuity. So, use of a double span purlin, for example. Or they may be reinforced by sleeves at the points of a high bending moment, which occur over the supports. In a so-called heavy end-bay system, the gauge of the member is increased in the end bay, and again that's done to accommodate the higher moment. In the normal gravity case, the top flange of the purlin is restrained by the cladding, particularly if the cladding is screwed to the purlins. However, in reversal, the bottom flange of the purlins are in compression, and the resistance then is increased by the use of anti-sag systems. Anti-sag systems have two functions. They certainly help to align the purlins, but secondly, they provide very important restraint in any reversal condition. There are various types of cladding, which may be aluminium or it may be steel, in a multitude of colours and in many different profiles. It may be built up on site with loose insulation, or it may be delivered to site as composite panels with a rigid core bonded to both sheets. And these types of cladding are generally screwed to the purlins. An alternative is a standing seam system, where the interlock between sheets is made at a special clip. The advantage is that there is no perforation through this type of cladding. The possible disadvantage is that the purlin may not be restrained. So moving on then to loading. Typical loads for a portal frame are that the permanent actions are somewhere around 0.2 kilonewtons per metre squared, and the services load ranges anywhere between about 0.1 and typically 0.25 kilonewtons per square metre. The imposed load on a roof will be taken from EN 1991-1 and its UK national annex, and typically will be 0.6 kilonewtons per square metre. We also need to consider the snow loading on a roof, so we would look at 1991-1-3 and the all-important UK national annex. The snow load depends on the snow zone and then is adjusted for altitude. And then there will be three cases that we need to consider. First of all, uniform snow on the roof slopes. Secondly, snow removed from at least one of the roof slopes, so that's an asymmetric load case. And finally, drifted snow, if there are valleys or parapets or other obstructions, or snow can blow off a high roof onto a lower roof. Drifted snow is described as an accidental combination of actions, and therefore there are reduced load factors when we consider that particular combination. We would take the wind loading from 1991-1-4 and again its UK national annex. We would take the basic wind velocity from the map. We would allow for altitude and for terrain. We would allow for the distance from the sea and the wind direction, and that would result in a peak velocity pressure. We then combine the peak velocity pressure with pressure coefficients. So depending on the direction that the wind is blowing with respect to the structure, there is a range of coefficients that we consider over different areas of the roof and over the walls. There are also internal pressure coefficients. These can be calculated based on the permeability of the walls and the roof, or the Eurocode says we can take both plus 0.2 and minus 0.3. We often need to consider dominant openings, and common practice, even if there is an opening which would be dominant, is to consider that opening to be shut at ULS. If we do that, there is a second case that we should consider, and that is the opening being open. and that's an accidental combination of actions, and therefore we would use reduced load factors. Secondly, because of the reduced likelihood of that event, we would reduce the probability factor to 0.8, and because the effect of that factor is squared, the peak velocity pressure then becomes factored by 0.64. So the combination then of reduced load factors and the reduced peak velocity pressure may mean that this secondary consideration with the openings open, it may mean that this is not critical. When we calculate ultimate loads, we can use expression 610 or the more onerous of the pair of expressions 610A and 610B. We should note that when we introduce a second variable action, the second variable action is additive. So if we take the example of a gravity combination, the gravity combination might be 1.35 times the permanent actions plus 1.5 times, let's say, the snow load. When we add wind into that combination, it's still 1.35 times the permanent actions plus 1.5 times the snow load. So the wind load is additive. It's factored by a load factor of 1.5, but also by a psi factor, which is a reduction factor and is specific to the type of load. Notice also that in some combinations the wind load will be factored by 1.5. So if we compare and contrast with previous practice, wind will be important. It always will be for portal frames, but possibly under the Eurocode system even more so. Now, according to EN 1991-11, on roofs, so we really are thinking about a portal frame, which is fundamentally a roof, imposed loads and snow loads or wind actions should not be applied together simultaneously. So if we think about the load combinations that we could consider, here are some of them. We certainly need to consider the first 5, although if we examine combination number 1 and combination number 2, one of them will be more critical. Either the imposed load on the roof or the snow will be larger than the other. Combinations 3 and 4 are almost the same, but in combination number 3, snow is the leading variable action and wind has the psi factor applied. In combination number 4, wind is the leading variable action and snow has the psi factor applied. But combinations number 6 and 7 are combinations that include imposed load and wind or imposed load and snow, and the Eurocode says we do not check those particular combinations. So preliminary sizing. If we knew no better, we could imagine that the rafter of a portal frame is like a fixed-ended beam. And if we analyse the fixed-ended beam, we know that the hogging moment at the end is WL squared over 12. A portal frame rafter is not exactly like a fixed-ended beam because there is some flexibility in the column. So therefore a reasonable assumption is that we calculate a lower moment, perhaps WL squared over 15. And this would be a reasonable assumption to calculate the eaves bending moment. If we want more precision, then we can use lookup tables, which will give us section sizes for the rafter and for the column directly. There are lookup tables for S275 steel and for S355 steel, and both of them are based only on the design vertical load. So that's the ultimate load on the rafter. For various levels of ultimate load on the rafter, and for various eaves heights, and for various spans, then we have section sizes for the rafter and for the column. If we consider the rafter, then the section size depends primarily on the span, and that's because the bending moment at the eaves concerns WL squared over, let's say, 15, and L, of course, is the span of the rafter. There are two forms of column, here described as restrained columns and unrestrained columns. A restrained column has the opportunity to introduce additional intermediate restraints to the inside flange. And that's very important because they will serve to increase the resistance of the column. If those intermediate restraints cannot be provided, and it may be that, for example, there are roller shutter doors down the elevation and therefore the side rail is interrupted and thus ineffective, then the column is described as an unrestrained column. The serial sizes for the unrestrained column are therefore significantly larger than the restrained column. So at this very early stage in the process, we need to decide whether these additional restraints are possible or not, and that will then define whether we should select a restrained column or an unrestrained column. If we wish to do some analysis, then a good rule of thumb is that the inertia of the column is 1.5 times the inertia of the rafter. We have formulae which are available, typically in publications such as the Steel Designer's Manual. We can put these into a spreadsheet if we wish, combine various loading scenarios, and that will give us the bending moments around the frame. Often, of course, we won't use formulas such as this. We will simply use plain frame elastic analysis, which is readily available to most designers. Moving on to analysis, we want to relate the real dimensions of the frame to the dimensions that we use in analysis. So the client may well describe the clear span, and that will be the distance between steelwork. The span which we will need for analysis will be the centerline span, so will be a little bit longer. The clear height is probably going to be defined from the top of the finished floor to the underside of the haunch. And we need to recognise that the base level is typically below the finished floor, often by around about 300 millimetres. And secondly, we need to have some rough approximation for the depth of the haunch. And normally, measured vertically, the depth of the haunch is approximately equal to the depth of the rafter. So we can calculate the nodal height on the centre line of the column. The haunch length is typically chosen to be about 10% of the span, although we must take a little bit of care if we're using bespoke software, because both the haunch length and the haunch depth can be defined in slightly different ways. One or two comments about the methods of analysis which are available to us for portal frames. Commonly available software for plain frames is likely to be elastic analysis. Traditionally, portal frames were designed using plastic analysis, and a plastic analysis looks for plastic hinges and looks for sufficient plastic hinges to cause collapse. That's the basic approach in a rigid plastic analysis. Commonly available bespoke software used specifically for portal frame analysis is going to be analysing using a combination of both elastic and plastic, known as elastic plastic analysis. So as well as identifying the plastic hinges which might cause collapse, it's also going to tell us about the deflected shape. And this elastic plastic analysis, probably including second order effects, is going to produce the most economic design. For all frames, including portal frames, we need to assess the significance of second order effects. Are they significant and need to be addressed, or are they small enough to be ignored? And generally, with a portal frame which is relatively flexible, we would expect that second order effects are likely to be significant. Second order effects in portal frames arise from two areas. Here is a frame which is subject to vertical load only, and under that vertical load the apex drops and the eaves spread. Perhaps if plastic hinges form, then there is a further and potentially considerable drop of the apex. So the final form of the frame is not the form that we initially analysed. If we think of a frame which is subject to vertical load and lateral load, then the vertical reactions at the end of the rafters are now eccentric to the base reactions, and this encourages the frame to collapse. Both of these effects are second order effects, and we must assess if they are significant or not. The significance is assessed by the value of a term alpha crit. Alpha crit will generally be calculated if you're using bespoke software. There are approximate methods given us in the standard, but those approximate methods are limited. They cannot be used when the axial load in a member is significant. In most portal frames, the axial load in the rafter is significant, and then we can't use the simple approach given us in the Eurocode. And therefore, an alternative expression is recommended, and that's to calculate alpha crit est. The first term, 0.8, allows for the compression in the column, and the second term in the bracket allows for the compression in the rafter. The final term, alpha crit, is the calculation of the story height divided by 200 times delta NHF. Delta NHF is the lateral drift at the top of the column when we analyse the frame just with notional horizontal forces applied to the frame. Note that these are notional horizontal forces and not equivalent horizontal forces. The notional horizontal forces are taken as 1/200th of the factored vertical reactions at the bases. When we calculate alpha crit or alpha crit est, it's highly recommended that we take the benefit of base stiffness even if we have a nominally pinned base. So we are encouraged to take the base stiffness as 10% of the column stiffness. If we're using bespoke software, we can probably input that value directly. If we are modelling using a plain frame program, then we probably need to include a dummy member. So the diagram shows how we would model a dummy member. It's rigidly connected to the column. It has a length of 0.75 of the height of the column. It's pinned at the extreme end, and it has an inertia which is 10% of the column member, and that will provide a base stiffness equal to 10% of the column stiffness. A little reminder that when we're analysing at ULS, the strong recommendation is to model with a perfect pin, otherwise we would need to take the resulting moments through the base plate and into the foundation. So to calculate frame stability, the step-by-step approach is, first of all, carry out a ULS analysis, assuming perfect pins at the bases. Note the axial load in the rafter and the vertical reactions. Consider if the axial force in the rafter is significant, and it's significant if the design force exceeds 0.09 of the elastic critical buckling load, pi squared EI over L squared. L in that particular calculation is the distance column to column. If the force is significant, which I consider to be very likely, then we should calculate the notional horizontal forces as 1/200th of the vertical reaction at the bases. Apply those notional horizontal forces at the column tops to the bare frame. It's recommended that we allow for the base stiffness, and we then take a note of the lateral drift at the column top, delta NHF. Then we can proceed to calculate alpha crit est. If alpha crit, or if axial force is significant, alpha crit est exceed a certain value, then second order effects are small enough to be ignored. That value, if we're undertaking elastic analysis, is a value of 10. So if alpha crit or alpha crit est is greater than 10, and we are undertaking elastic analysis, second order effects can be neglected. If we are undertaking plastic analysis, we need to turn to the UK National Annex, because the UK National Annex gives us the limits when second order effects are small enough to be neglected. In the gravity combination of actions, that limit is 5. So in the gravity combination of actions and limited to certain frames, there are some geometric limits. If alpha crit or alpha crit est is greater than 5, then we can neglect second order effects. For all other combinations of actions, so typically those would be the combinations including wind, the limit is 10, and if we are to ignore second order effects, then alpha crit or alpha crit est must be greater than 10. If As will commonly be the case, second order effects are significant. Then we can amplify the actions simply by a ratio, and the ratio is alpha crit divided by alpha crit minus 1. Typically, if we find that alpha crit is greater than about 15, in my view the frame is probably a little bit conservative. A value around about 8 is more typical for well-designed frames. If alpha crit is below 3, then the Eurocode says that the approximate methods given in the standard are no longer good enough and we must do a second order analysis. In my opinion, if alpha crit is down towards 3, then probably we need to think about increasing the members in our frame. So having considered loading, having considered frame stability, maybe having amplified our loads to allow for second order effects, so therefore having determined the final design moments and forces around the frame, we can proceed to verify the members. So we need to verify the columns, the rafters and the haunch. They're all relatively complex because all those members are subject both to compression and to bending. And with all those members, the restraint positions are absolutely critical. So in the normal gravity combination of actions, if we consider towards the apex of the rafter, the outside flange is in compression and therefore the purlins are doing a good job of restraining that member. For the rest of the rafter, so in the haunch zone and down the column, the inside flange of those members are in compression, and if we did nothing else, they would be entirely unrestrained, and we need to be very careful of that situation. Normally, we would provide restraints from the purlin or from the side rail, and typically we would do that using diagonal braces to the inside flange. If we have carried out a plastic analysis and design, then there are special rules how we must restrain plastic hinge locations and where the next restraint adjacent to a plastic hinge location must be. If we are undertaking elastic design or for the verification of members which are distant from a plastic hinge, then we have some expressions to satisfy, expressions 661 and 662, which are both elastic verifications. However, the third term in both of these expressions is the minor axis moment divided by the bending resistance in the minor axis. In portal frame construction, of course, we don't have a minor axis moment, and therefore these interaction expressions reduce rather and consist just of two terms. We need to calculate the in-plane or the major axis flexural buckling resistance and the minor axis flexural buckling resistance. We need to calculate the lateral torsional buckling resistance, and we need to determine the interaction factors or the K factors. So first of all, considering a column, the first thing to say is that restraint at the junction of the underside of the haunch and the inside of the column flange is absolutely essential. So in everything I now go on to say, it's assumed that there is a restraint at that position. All the original research assumed that there was a restraint at the junction of the inside of the column flange at the level of the bottom of the haunch. As far as the column is concerned and major axis buckling, there are no restraints to major axis buckling, and therefore we would have to consider the full column length. In the minor axis, the side rails will be doing a good job of restraining the column, so if they exist, we would check between those restraints. If not, we will be using the full length from the underside of the haunch down to the base. Lateral torsional buckling is the same. We might be checking between torsional restraints, so that would be a restraint to the inside flange, if those are possible. If not, again, we will be assessing lateral torsional buckling from the underside of the haunch right down to the base. Note that the bending moment diagram is a triangular bending moment diagram, and therefore we could take advantage by using the higher C1 factors, when we calculate the lateral torsional buckling resistance. As far as the column is concerned, again we would need to consider in-plane or major axis flexural buckling, and that will take place over the full length of the rafter. Minor axis buckling will be between the purlin positions. Lateral torsional buckling will be between torsional restraints, and there are two major zones. Adjacent to the apex, where the bending moment diagram is close to being uniform, and adjacent to the sharp end of the haunch, where the bending moment is generally large but nevertheless is falling rapidly, and again we could take advantage of a higher C1 factor when we calculate the lateral torsional buckling resistance. Adjacent to the sharp end of the haunch, we need to be very careful and judiciously place restraints to the inside flange. So looking in a little more detail, it's very common to have a restraint at the sharp end of the haunch, and we will generally be assessing the lateral torsional buckling resistance to the point of contraflexure or to a point of restraint, which might be an intermediate purlin where we have provided restraints to the inside flange. Adjacent to the apex, the bending moment diagram is generally quite close to being uniform, and we will assess that between purlins. It may be that as we verify the various members, we may need to change the position of the restraints. It may be that we need to provide additional restraints to the inside flange. This diagram of a partially complete structure shows around the haunch area narrower spacings where the bending moment is relatively high, over the mid-length of the rafter relatively wide spacings where the bending moment is relatively modest, and again in the high bending moment zone as we approach the apex it would appear that the purlins have been spaced closer together. Having looked at the column and the rafter, we can then consider the haunch. The Eurocode does have clauses that we might use to determine the stability of the haunch, although they are for haunched members that contain a plastic hinge. We can use those because if we determine that the haunch is stable using a plastic check, then certainly it will be stable if our haunch is elastic. Alternatively, and conveniently, we can use an equivalent compression flange approach. And then we take the compression flange of the haunch plus a third of the compressed depth of the web, and we say that's equivalent to a T-shaped strut, and we simply check the resistance of that strut between restraints. And that approach can be very convenient. The gable columns are beams which span vertically from the base to the rafter. There will be two design conditions. First of all, with pressure on the outside and very possibly an axial load, but when pressure is on the outside then the side rails are restraining the compression flange and therefore increasing the lateral torsional buckling resistance. The second design case is when we have suction on the outside and again probably an axial load, but the compression flange is now the inside flange of the gable column, and unless we do anything else about it, is unrestrained, and therefore this design case may be the critical case. The bracing may be designed to act in compression and in tension, or in tension alone. The roof bracing collects the forces from the tops of the gable columns and any forces in the purlins, which may be due to restraint or from frictional drag on the roof, and it carries that force to the eaves level. The vertical bracing then conveys that force to the foundations. The eaves member may carry the force from the roof bracing to the vertical bracing if that's located in a different bay, but will also provide stability for all the portal frames. Some comments then on critical detailing, and I've already emphasised that the junction between the inside flange of the column and the underside of the haunch must be restrained. There are a number of ways to do that. Commonly, we might position a side rail at that level and provide diagonal stays to the inside flange of the column. Or we may provide a hot finished member at that location. It would need to be nestled adjacent to that inside flange to be effective, or we might provide restraints from the first purlin up the rafter. But one way or another, it is very important that that location is restrained. The location of the restraints to the inside flange of the rafter is also very important. Adjacent to the sharp end of the haunch, the inside flange of the rafter is in compression, and it's very likely that we will need to provide some additional restraints. That's the gravity load combination. In the reversal combination, then over the haunch length and adjacent to the haunch, then the compression flange is the outside flange, and the purlins are providing adequate restraint. But now the unrestrained flange is the inside flange adjacent to the apex. And it's very likely that we would need to provide one or more restraints in that zone. Perhaps we don't need to provide as many as adjacent to the haunch because the bending moment diagram is rather less. So a typical restraint layout would have a number of restraints around the haunch and one or more restraints adjacent to the apex. Intermediate restraints to the inside flange of the column are quite important. If the side rail is interrupted, for example by a roller shutter door, then an interrupted side rail does not provide adequate restraint. So at the early stage, one would need to be careful to assess whether additional restraints are possible or not. The eaves connection is always going to be substantial. A simple rule of thumb is that the end plate is likely to be 20 millimeters thick and associated with M20 grade 8.8 bolts, or it might be 25 millimeters thick and typically associated with M24 8.8 bolts, or even thicker, perhaps with M30 bolts. Because a universal beam section is being used as a column, and because the bottom flange of the haunch applies a substantial load, it's likely that a compression stiffener will be needed to reinforce the web. The compression stiffener, as a rule of thumb, is at least as thick as the haunch flange and at least as wide. Because the connection is carrying tension around the tension bolts and compression around the compression stiffener, then shear in the web panel of the column may be a problem. And if shear is a problem, it may be necessary to introduce a Morris stiffener to reinforce the web. Similar sort of comments for the apex. It may have a haunch or it may be a simple extended end plate, 20 millimeters thick with M20 bolts or 25 millimeters thick with M24 bolts are typical details. That haunch, even if it is a haunch, is usually neglected in the analysis of the frame. Turning then to fire design, the only situation where we need to worry about fire design is if our portal frame is adjacent to a boundary, because if members are only supporting a roof, the building regulations say that no special provisions are required. So there will be a consideration about how close our structure is to a boundary, because the obligation is to prevent fire spreading from our structure to the neighbouring structure. That situation is controlled by a three-stage process. We would generally provide fire-resistant cladding on the relevant elevation. We would fire protect the column up to the underside of the haunch so that we know the column won't collapse, and we would provide a moment-resisting base, because it's presumed that the portal frame rafters will lose strength, they will form a catenary, and they will apply a horizontal force at the top of the column, and the column base must resist this overturning moment. So there is a publication which gives full details. That's a publication P313, and you can see the general philosophy that if a fire occurs within a portal frame, the rafter loses strength as it warms up, it starts to collapse, it forms a catenary, and in doing so applies an inward horizontal force at the top of the column, and that's the overturning moment which must be resisted by the base. There are relatively simple design assumptions which determine the size of that horizontal force and therefore the value of the overturning moment. For other forms of construction, so for gable columns and for monopitch frames, then really it's engineering rules of thumb which are given in the earlier publication. For the structural engineer, the key requirement is to provide a moment resisting base. If we provide a moment resisting base, it may be that the base plate is thicker, it may be that we need to provide additional holding down bolts, and in extreme cases we may need to provide a small haunch. Despite those modifications to the base, which are clearly making the base stiffer, common practice in the UK is still to presume that the base is nominally pinned when we carry out the ULS analysis. So in a fire, it's assumed that some of the cladding will burn off, the rafters lose strength, as can be seen in this particular photo, and go into catenary, and it's the horizontal force as a result of that catenary that the elevation columns must resist. So here is another example of rafters going into catenary. This building has been partially demolished, but the columns on the left hand side have remained, broadly speaking, intact. Finally then, serviceability, which is all about deflections of a portal frame. There are deflection limits, and generally we would concern ourselves with lateral deflection at the column tops, and perhaps even more importantly, relative deflection between portal frames. Relative deflection may be the critical check, particularly if we have a gable frame which is constructed from gable columns and simply supported rafters, which will not deflect, but the adjacent portal frame may deflect, and we need to check the relative deflection between the two quite carefully. The limits depend on the type of cladding, so if we have a flexible cladding, the limits are not so onerous. If we have a cladding which is relatively brittle and therefore may crack, then the limits are more onerous. There are limits given in the publications for portal frames to both BS 5950 and the Eurocode. Remember, when we are checking deflections, a very useful technique is to allow for the stiffness of even a nominally pinned base, and if we do have a nominally pinned base, the recommended approach is to allow 20% of the column stiffness, and that will do a good job in reducing the deflections. So the design guidance then that's available covers both design standards. So publication P252 covers design to BS 5950, and publication 397 covers design to Eurocode 3. My concluding remarks are then that a portal frame is a very common form of construction, and rightly so. It's structurally efficient, it's lightweight, it's cost effective. There are mature design rules which are appropriate for the design of portal frames. Often we would use bespoke software, and that will produce a very competitive design. There are some things that we do need to pay careful attention to, particularly unrestrained flanges. We need to be aware that under different combinations of actions, notably reversal, then other flanges may be unrestrained compared to the gravity combination of actions. We need to consider carefully at an early stage whether or not we can introduce additional restraints to the inside flange of a column, and we always need to provide a restraint to the inside flange of the column at the level of the underside of the haunch. When we need further help or when we need further detailed guidance, there are comprehensive design guides available, both with comprehensive numerical worked examples. That concludes the presentation. Thanks for listening.